So today we're going to move away from static electricity. We're going to talk more about current electricity, which is the more useful way of looking at electricity because it's how we use all of the electric devices that we use in our day-to-day lives. So we're going to look at the concept of electrical current today. We're going to look at how electrical current works, but we can't really go into it in too much detail without talking about the characteristics of electrical current. So there's three main ones we're going to focus in on today: voltage, amperes, and resistance. We'll also, of course, look at electrical circuits today. We're not going to look at it in great detail. That's something we'll save for later on. Let's get started. So, electrical current, first things first. An electrical current is a continuous flow of electrons from one atom to the next. This is different from static electricity, where electrons are simply given or taken and then stored in an object until a discharge occurs. Now, current electricity only works if two conditions are met, and this is super, super important. In order for current electricity to happen, you need to have an energy source to cause those electrons to move. There has to be something that's actually doing this here, right? The other thing that you need is current will not flow unless there's a complete path. So you need something called a circuit in order for those electrons to actually flow. So what's really important to understand here is a current is a continuous flow of electrons here. So it's the electrons that are moving from one atom to the next. And if it's a continuous flow, so not just like a one-off thing and then it stops, if it's a continuous flow, then it's an electrical current. This isn't to be confused with the whole idea of static electricity, where if you like rub your feet against a carpet and then touch something that's metal and there's going to be a little zap that occurs. That's not an electrical current. That's just a very swift discharge. It isn't continuous. It just happened in a very quick snap, right? That's all that happened. All right, so next up, if it's going to let me change slides here, this is interesting. There we go. Okay, so electrical characteristics. There's three main characteristics of electricity that we need to understand, and I'm going to kind of slow things down here because this is where things get a little obscure. The first one we're going to talk about is amperage, which is used in a formula with the letter I. Now, amperage is a measure of the current, and its units, of course, are just in amperes, more commonly just known as amps. So an amp is just a measurement of how much current there is. So in other words, just how many charged particles are going through your circuit at any given time, right? So amps is just the current, the speed of the current, basically, right? Now, voltage is one that's a little bit more obscure, but it's one you've almost certainly heard of before. Voltage is a measure of the potential difference. And that doesn't mean much to us, at least not quite yet. But in other words, voltage is the measure of electrical energy that each charged particle holds, right? So as those charged particles are going through the circuit, the voltage is just how much energy that each of those particles holds. Now, the units for voltage, not a big surprise, are volts. We're going to get into that one in more detail in a moment. The last one that we need to know in your textbook, at least not in this section, hasn't referred to it, but I thought we really should bring this up right now to make it clear, is resistance, which of course is the capital R when it's in a formula. Now, resistance is the ability of an object to oppose an electrical current. This is measured in a unit called ohms. We'll talk about that a little bit later today. Just to be a little bit more clear, something that has a high resistance, for example, would be rubber, right? Rubber does not allow electrical current to flow through it very easily, so it would have a high resistance. So there's a ton of ohms in rubber, you could think of, right? So you could use that measurement of ohms to describe rubber. Now, copper, on the other hand, copper has a very low resistance, which is why it's so useful for sending an electrical current through, right? We use copper wires to wire our homes, for instance. And that's because it has a low resistance. Now, you can relate these three characteristics mathematically. We won't have to do this, at least not quite yet, but the formula for this is V is equal to I times R, right? So the voltage is equal to the current times by R, the resistance. Now, just in case you're wondering, you know, volts was V, resistance was R, but why is I, like I is current? You'd think it'd be a C there instead. Well, apparently the reason is current is denoted by I because it was originally thought of as being the intensity. And that still actually is a good way of thinking about current. Current is basically just how intense that electrical circuit really has, right? So in other words, just how much intensity is in there. That's a good way of thinking of current. But we'll get into that a little bit later too. So here's another way of thinking about it, because oftentimes the relationship between these three things is kind of hard to understand. This might work for you, it might not work for you. If it just confuses you more, I apologize. But one way of thinking about this is thinking of voltage as just being the pushing factor. So if you had a high voltage, this guy right here, the push, would be really strong. There'd be a lot of like push and oomph behind this. Now, amps is just basically just how much is getting through. Now, in this picture, of course, there's not much of this guy getting through, right? He's trying to make his way through this, pipe or whatever. So there'd be really low amperage here. But if there was a lot of people coming through, for instance, so a lot of flow, that would be the amperage. So just the amount of stuff that's getting through the circuit, that's your amperage. Now, ohms, of course, this was resistance. Resistance, again, is just how much we oppose the flow of electric current, right? So a really strong resistance, so a really high amount of ohms, is going to be doing a pretty good job at preventing a lot of these amps from getting through, right? So basically, it's just this big competition between volts and ohms, so your voltage and your resistance, in order to influence how your amps go through. Amps are pretty much just a resultant variable from these two, but not always. That's just an oversimplification of it. It really is a relationship between all three of these things. So another analogy, of course, is with water. I think I actually have a poster in my room of this one up in the top left. If you prefer to think of it as water, the water pressure is the voltage. Okay, so just in other words, how dense that water is being pushed through the pipe, that's the voltage. Now the water flow, in other words, how much water, so how many water molecules, I guess you could think of, how much water is actually making its way through the pipe is your amps. Okay. Now the pipe size would be the ohms, right? So this is a very thick pipe. There's not very much resistance here. This is why it's kind of a bit of a backwards example, right? So a really big pipe would be a really low resistance. The water is going to flow through here, no problem. But if you shrunk this pipe down, like especially if this pipe went smaller and there was just like a little narrow little opening with the same amount of pressure in the pipe, that's going to have a big influence, of course, on the flow of the water, right? Now, anyway, energy created is wattage. We're not going to talk about watts quite yet, so you can ignore that part of this. But yet another analogy, again, building off the water one. If you had a hose with water coming out of it, of course, if you increase the pressure, so the amount of pressure that was actually in the water itself, you'd be increasing the water flow. Now, I don't know about your house, but the house that I grew up in, if there was more than one person using a tap in the house at one time, the water flow would go way down. And that is actually a result of the pressure, right? And if you want to think of this in terms of electricity, it's the same idea. If theoretically, now electricity in my home didn't work like this, thankfully, but if theoretically many people had many things plugged in at one time, maybe there would be a reduction of pressure, right? There wouldn't be as much pressure to go around, so you have a reduction in your flow. So again, there's a good correlation between water and electricity, at least in terms of an analogy here. That's an awful double-sided arrow. Let me try that again. That's a bit better. There you go. So there's an analogy that kind of goes both ways with this. More pressure means more flow, and that's the same with voltage and current. More voltage, which is your equivalent to pressure, equals more flow, which is your current, right? All right, moving on. Okay, so I'm going to break down these in a little bit more detail. Some of this will probably sound a little samey, but whatever. Amperes are a measure of current, or in other words, the rate at which the electrical current flows through the circuit, as I've already mentioned. Now, different household appliances will use a different amount of amps. And of course, this is controlled by things called resistors in there, because we'll get into that a little bit later, but of course, you want to change the resistance and that'll change your amps. Now, light bulbs, just in case you're wondering, generally use about 0.5 amps, so half of an amp. Microwave ovens, however, they need to use between 5 amps and 8 amps, right? So the amount of current for a microwave to work is actually a bit more. Now, an electric kettle, this one actually surprised me. I didn't think it'd be more than a microwave, but an electric kettle uses about 13 amps, right? So the amount of amps by different things changes. Now, also, one thing that's kind of interesting about amperes is amps are generally considered the most dangerous aspect of electricity to human health, right? Amps, of course, are the part of electricity that would be more likely to, of course, kill you, right? Now, it actually doesn't take a lot of amps to severely harm a human being. This little picture that I found online, of course, kind of shows it in milliamps. Now, a milliamp is 1,000th of 1 amp. So in other words, this right down here would be 0.001 amps way down here. Basically, at that many amps, that's where you're first going to start feeling something. At about 2 milliamps, so 0.002 amps, that's where you feel like a little shock, okay? If you had 10 milliamps, or in other words, 0.01 amps, so 1/100th of an amp, you wouldn't be able to let go of that thing, right? It would be shocking you so much that your muscles wouldn't be able to overcome it. 20 milliamps, of course, you get muscle contraction. Suffocation starts becoming possible if you're hit with 30 milliamps, that's 0.03 amps. And your heart would actually stop beating at 100 milliamps. Now, 100 milliamps is only 0.1 amps. Compare that to what just a light bulb uses, right? That amount of electricity flowing through a light bulb, if you were hit with that amount of amps, that would be a very, very, very bad thing, right? Breathing can stop at 300 milliamps. 900 milliamps produces severe burns. And at about 1 amp, which again lights a 100 watt bulb rather than like a standard 0.5 amp bulb, but whatever. That's a totally different conversation there. At 1 full amp, that's where things start getting to be closer to fatal. I know for sure the number that's always sat in my head is 2 amps is pretty much a death sentence right there, right? So 2 amps is pretty darn fatal, right? Now with your heart stop beating, of course, you can resuscitate someone from there, but 2 amps can be bad news. Now, not always, of course. There's different factors that play into this. Of course, voltage and resistance comes in. We'll talk about that in a bit. But amperes, generally speaking, most people would agree that's the most dangerous aspect of electricity to human health. All right, now on to voltage. Volts are a measure of potential difference. This can be a bit tough to really comprehend. Maybe I'm at least projecting my own, feelings on voltage here. Voltage has always been something that's hard for me to wrap my head around, and probably for you too, but we'll see. Now, it's often easier to think of voltage as being your energy per charged particle, right? In other words, it's how much oomph each charged particle carries, right? So high voltage is a high amount of oomph, okay? Now, voltage is what pushes the charged particles. Just in case you want some references, here's a AA battery, and I think a AAA battery too, generally delivers about 1.5 volts. And it even says on the side of the battery right there, 1.5 volts. Now, a regular electrical outlet that we have in our house would deliver about 120 volts. Now, there's different types of electrical outlets. I know the ones like in a laundry room for a washing machine or a dryer, they're going to actually deliver more volts than that, but just your standard plug is 120 volts. Fun fact, by the way, in different countries, they have different amounts of volts for their plugs. That's why when you go to different countries, you need like adapters and stuff, and you're not supposed to like plug your plugs in. And oftentimes our plugs look totally different than our plugs, but we'll get into that another time. Now, just for a fun fact, static electricity, like when you touch something metal, when you got a static charge on you, that can actually deliver over 10,000 volts. However, because that's not a continuous current, which in other words, there's very low amperes, it isn't dangerous, right? It's gonna zap you and you're gonna go, ow, but it's not a continuous current, so it's not gonna prove damaging to you. So just because there's a high voltage doesn't mean necessarily that it's dangerous. Generally speaking, there is a correlation because high voltage is dangerous, but not because of the voltage itself necessarily, but because the formula V equals IR says that if you have a high voltage, that can actually create a high current. Let me put it this way. Your body has an inherent resistance. We're made of matter, of course, so our body's going to have a certain amount of resistance to it. If we increase the amount of voltage and your resistance isn't changing, the only way for this formula to stay balanced, if you thought of this as like a balanced scale, this is going up, this is staying the same. To compensate for it, that means the current has to go up, right? So a higher voltage means a higher current because your resistance in your body doesn't really change. So that's why this can be dangerous. You have a higher voltage that's applied to you all of a sudden, that can increase the amount of current that's flowing through you. If you thought of the analogy of the people in the pipe, right? Someone stronger pushing is going to push more people through. That's another way of thinking of it. Now, measuring voltage, we'll go through this real quick. Voltage is often measured using something called a voltmeter. Now, even more commonly, however, people use some device called a multimeter. A multimeter is just a device that can measure more than just voltage, right? There's often a way to measure amps and often another way to measure ohms, right, which is resistance. Now, how it generally works is you basically have these red prong and this black prong that are plugged into your multimeter or your voltmeter. And then there's a dial here that you can select different measurement strengths, right? So the meter here will actually spit out different measurements. So if you had like a really low voltage, you'd set it to the really low voltage setting. But if you were measuring something with a higher voltage, you'd set it to one of the higher voltage settings. That's basically all you got to worry about there. Then you take your red prong and you put it to the positive end, and the black prong you put on the negative end. Sometimes it's hard to tell, what's your positive end and what's your negative end, but don't worry about that for now, right? Now the meter is just going to output the voltage on the display. And of course, if you're dealing with something with a higher or a lower voltage, you need to change the dial accordingly, right? That's how they generally work. Again, notice a multimeter is kind of cool because it can measure ohms, which is resistance. So in other words, you wouldn't even need an electric current. If you just wanted to like figure out the resistance of a wire or something, because this has a battery in it, it can provide a very small amount of current so that you can apply it to something that provides resistance, like a wire, and measure the resistance of that wire as well. Anyway, I'm rambling. You don't even know that. All right, speaking of resistance, resistance is measured in ohms, which is denoted by the Greek letter omega. It's this funny little symbol here, and I usually like draw it by going from left to right. It's kind of like like an O that like someone like broke open the bottom and then sat on, so like the sides kind of split. I don't know. Anyway, so in the formula V equals IR, a high resistance, so if you're increasing your resistance, will result in a lower current, generally speaking, right? Your voltage could be staying the same. If you increased your resistance, then to keep this formula all balanced, you'd have to bring down your current, right? So if you increase the resistance, your current is going to go down. And again, thinking of the pipe example, an increased resistance means a tighter pipe, right? So this is maybe a tighter pipe, this is a looser pipe, this is a higher ohms, right? Because it's a smaller pipe, okay? There's more resistance. That's why I may be thinking of the guys, like the guy pushing, the guy going through the pipe, and then the guy on top with the lasso or whatever. That might be a better way of thinking of it, because a stronger resistance produces a smaller pipe, okay? Now, dry skin has higher resistance than wet skin. That's a good reason not to deal with electricity with wet hands, because put it this way, wet hands have low resistance. Low resistance means higher current, right? So if this went down, this would have to go up. That's why it's better to deal with electricity when you have dry skin, of course, needless to say. Now, a resistor is a device used in circuits to reduce or control the amount of current that flows through the circuit. And they're very kind of weird looking. And this picture is actually kind of deceiving, because usually resistors are really small, like the size like the tip of a pen. But they can look in like all these different colors and stuff. And the color codes, of course, tell you how strong the resistor is. You can also use a multimeter to determine that. But basically, a resistor is just something they put in a circuit to control that amount of current going through it, right? Anyway, that's all you need to know about those. Now here's just a picture. I was trying to think of some electric device that would have it, and I looked for something a little bit more modern. Modern resistors often aren't quite as, like, they don't have that same distinguished look as these guys do, right? So what I ended up finding was, this is a picture of a Game Boy that someone took apart. And just by looking at this, again, I'm not an electrical engineer by any stretch, but I looked at the circuit here and I was like, okay, let's see if I can find a resistor. Didn't take me 2 seconds. I found one right in the bottom right-hand corner, just way down here, of course. So I zoomed in on there. I know it's not the clearest picture, but that right there on the circuit board for this Game Boy, there's your resistor right there. Most electric devices, of course, are going to have a resistor built into there somewhere to control the current going through it. Now, the power source for a Game Boy, of course, is a couple AA batteries. But sometimes with that amount of voltage that's going through those batteries, they want to control the current for different uses within the device. It gets very complicated, of course, but the basic idea is resistors are used in a circuit. This is a very complex circuit, obviously, to control the current. Okay? Anyway, moving on. Now, speaking of circuits, we're almost done here. Electrical current flows through a circuit. Remember, in order for current to flow, you need two things. You need an energy source, whether that's a battery or whatever, and you need a complete circuit. Okay, so in other words, an incomplete circuit is not going to result in an electric current. Okay, now generally, electrical circuits contain at least three things, and these three things are pretty basic. Like, this would be a very simple circuit. The main thing is a conductor. Basically, this is just your wire. Now, it doesn't have to be a wire. Believe it or not, you can actually use certain gases as conductors. Electricity can pass through gas. If you ever see like a fluorescent light bulb, those are like those long ones that you usually would have like in a classroom up top. There's a prong on this end and there's a prong on this end, so electricity comes in one end. And what happens is that electricity flows through the bulb, but there's no wire through the bulb. It's just filled with a gas. So the electricity passes through this gas to the other end to complete the circuit. And that's how those fluorescent light bulbs work. Okay, so again, a conductor, usually a wire, doesn't have to be though, it can be a gas as well. Now, an energy source, this one's obvious, it's either a battery or an outlet, right? So in other words, you need to have something that's providing that energy. We're going to talk about the power from batteries a little bit later on, because again, that is a whole different conversation, but just understand that's a source of energy, shouldn't be a big surprise to us. The last thing that a circuit needs is a load, right? So a load is just a useful device. Otherwise, why would you have a circuit? What's the point of making an electric circuit unless you have some sort of device, right? So a load, a good example of a load, of course, would be a light bulb. Notice that the light bulb itself has a circuit within it. So in other words, there's a conductor within it. But of course, that conductor is often designed in a different way so that it's producing something that we want to use. Same with this fluorescent light bulb I drew as well. Yes, the light within the fluorescent light bulb is part of your conductor, but it also is designed in such a way to fulfill a different purpose, namely producing light. Now, the whole big thing I want you to take away from this, like really big idea to take away from this, is the load turns electrical energy, the energy from that voltage, into another useful form of energy. You might remember from previous science classes that energy cannot be created or destroyed. It can only change form. Your electrical energy doesn't disappear. You're using your electrical energy to produce something you want. So in terms of this light bulb, you're using the electrical energy to produce light and also, of course, a little bit of heat. Now, maybe you didn't want the heat from the light bulb, depending on what you're using the light bulb for. But of course, the light is another form of energy. One last thing I'll say about this is, again, coming back to the two things you need for current to flow. Not only, of course, do you need the energy source, but you also need the complete circuit. So this picture was actually quite nice because it shows a completed circuit because there was a switch right here and the switch closed means your circuit is now complete. When that switch is open, however, there's a break in the whole circuit. You're not going to have any energy flowing through that at all. There's no electricity going. So in other words, because that circuit is not complete, you're not going to have an electric current. Okay, that's why switches are so important because it controls that for us. I guess the last thing that I didn't mention on there, like light bulbs convert electrical energy to light and heat. The next thing that came to mind, literally because I have one right next to my desk here, is a fan. Fans, of course, turn that electrical energy from the plug into kinetic energy. In other words, moving energy. So energy of something that's moving, right? What's moving, of course, is the fan blades. Now the fan blades moving is creating basically a push in the air, and that's pushing the air, so it's giving kinetic energy to the air, so the energy is just being transferred from one thing to the other, so it's going from electrical energy to energy within the fan, and then the energy in the fan is being transferred to the air, which is forming wind, which cools you down, right? That's basically all that's happening. All right, I think this is the last thing we're going to talk about, circuit from power plants to home. You probably have a pretty good idea of how this works, but just in case you don't, here it is. Basically, of course, we have power plants that generate electricity. Not a huge surprise, right? There has to be some like ultimate source. Different kinds of power plants. There's solar plants, there's nuclear plants, there's wind plants, there's coal plants, all these different kinds of power plants that generate electricity in different ways. We don't have to worry about that right now. But basically, the electricity comes from the power plant. It goes to something called a transformer. This is what they look like up in the top right-hand corner. And what that does is it transforms it to turn it into a higher voltage so that it can be transmitted better, right? So it gives it way more push, like gives it a huge surge of push, and then that sends it through the transmission lines. So of course, those big electric lines that you see all over the place, especially along highways and stuff. And then those make their way into neighborhoods where there's usually a neighborhood transformer which steps that voltage down, right? So it reduces the voltage and makes it a little bit better so it's usable for your home. So generally speaking, like that 120 volts that you would get from your electrical outlet in your house. Now those transformer boxes in a neighborhood, we're hopefully all familiar with those. There's one right outside the school. They're usually those green boxes that kind of hum, right? You kind of should stay away from them. And there's like signs all over that say like danger, high voltage, and all that. But again, that's what that's doing. It's stepping down the voltage so it can be used by that household. So then you have your distribution lines that, of course, carry the electricity to the house. And there's also transformers on the poles that step down electricity before it even enters the house as well. So there's several stages of this where they control the voltage and the current. All right, we're done. That was a long lesson. I apologize for that, but page 283, questions 2 to 4, and then 6 and 8. So there's not very many questions to do on this one. I kind of handpicked them. As always, if you have any questions, please let me know.